Swayam Prabha. Digital India. Educated India.
Welcome to this course on principles of molecular dynamic simulations. I am myself Dr. Ethayaraja, Associate Professor of Chemical Engineering at IIT Madras, Chennai. So, in this class, I will discuss the motivation and scope of doing computer simulations. So, if you look at methods of scientific investigation, that means when you want to study a particular phenomena, physical phenomena or a system, you basically resort to various means of doing this. The one aspect is to do experiment. So you basically consider a system and then use a set of apparatus and materials, and then you control certain variables and then manipulate certain other variables, and then look at how the system responds. And then using various analytical techniques and instruments, you could look at how the system responds, and then you can collect factual information of the system. So it's basically doing experiments means observing the system's response when you change certain variables, and then you collect all this information. So this is one way of studying a system scientifically. The other way of doing this is doing what is known as theoretical investigation, where you collect all these facts which is available empirically or experimentally, and then you try to coherently put them together into a pattern, and then draw some physical laws that will characterize the system's behavior. This often uses a mathematical deduction and analysis, and then sometimes even numerical evaluation also. So traditionally, scientific investigation have been taking place either via experimental methods or by theoretical means. Now, each of these methods, even though they have their advantages, they also have some shortcomings. For example, if you consider experiments, many times the condition with which we want to study the system are sometimes difficult to control. This may involve high temperature, high pressure conditions or extremely harsh conditions. Sometimes even the measurements themselves may be very difficult to make because we may not have the right set of instruments to make measurements. And even if you could do measurements properly, sometimes even the results are very difficult to interpret. The physical meaning of the results sometimes difficult to interpret for us. And similarly, if you look at theory, the theoretical deduction mostly happens with the limiting assumptions. For example, we make assumptions that the system is behaving linearly, so we apply linearity principles. Sometimes we expand power series expansion of certain variables. We also assume a high symmetry, and we often have a very small number of parameters that goes into this theoretical approaches. And we also make a lot of simplifying assumptions so that this theory becomes reasonably simple enough so that it can be subjected to mathematical analysis. So on one hand, we see that experiments have certain limitations in controlling, measuring and interpreting the results, whereas in the theoretical perspective, we often limit to very simple cases because of various underlying assumptions. So now, these computer simulations have become yet another way of doing scientific investigation, because in this case, we make use of computers and simulation programs to investigate a system. So this has become a medium of research to bridge the gap between theory and experiment. In places where theory or experiment is not very strong, you can actually resort to doing this experiment in a computer, and we can make use of computer to investigate a particular system. And what we are actually hoping to get by doing computer simulation is that we would like to understand the microscopic level details of a system or a physical phenomena. And we also hope to get some prediction of experimental observations as well. So in other words, you can think of that a combination of experiment, theory and computer simulations. So when you have a system investigated by all these three methods, we can actually hope to get a far more effective understanding of physically useful results and phenomena than by doing just one of them or a pair of them. So if you look at many of the research articles that are coming up in the recent times, you will see a combination of experiment, theory and simulation all kind of give their own understanding to the same problem. So that is the scope of doing computer simulations in science. So now I was talking about computer simulations. So it's a very broad term which involves various kind of techniques. But in this course, we would like to discuss about molecular dynamics, which is a special case of computer simulations, which also uses computers. So the way we do this computer simulation, here I have given some simple examples. So you often take a simulation box, a cubic box, and then you basically throw in certain number of atoms and molecules. The blue spheres that you see here are basically a set of atoms or molecules. And then we try to calculate the forces acting on each of these molecules. And these forces can stem from various origins, physical origins. So they can be of electrostatic interactions or van der Waals interactions or hydrophobic interactions. So as long as you know what kind of interactions are acting between these atoms and molecules, you could actually calculate what are these net forces. Once we know the forces, then we can actually use a system of equation of motions, which could be Newtonian or Lagrangian or Hamiltonian, and then we can numerically solve them. So what I mean by solve them is that you're basically dynamically solve the time and the position and the velocity of the particles in time. And then by that, you can actually see how the system evolves in time. Okay, and using these microscopic variables such as velocities and position of all the atoms as a function of time, we can actually detect various measurements. We can make a lot of measurements and try to understand the system's behavior as it evolves. So this is the crux of doing molecular dynamic simulations. And in this course, we are going to see various aspects of doing such simulations and various practical details also we are going to discuss. Now, this way of doing computer simulation or molecular dynamic simulation has been envisioned by the great scientist Laplace in his treatise on philosophical essay of probabilities, which was published in 1812 in French and later on translated in English. He basically hypothesized the following. This is a very long sentence, but I will read it for you and then I'll try to decipher what it means. It says, given for one instant, okay, so that means at any given point of time, an intelligence which could comprehend all the forces by which nature is animated. So that means you're looking at some sort of intelligence. He is not using the word computer or any other daemon. He's talking about some intelligence which can understand all kinds of forces acting between these, all the forces acting in nature, by which the nature basically evolves in time, and then the respective situation of the being composed it. That means whatever that nature is composed of, atoms and molecules and all the things, and if this intelligence can actually comprehend where these atoms and molecules are and what are the forces acting between them, if such an intelligence exists, and that intelligence should be sufficiently vast to submit these data analysis. That means you're going to look at a very large number of atoms and molecules in the entire nature and the number of different kind of interactions and forces that are acting between them. So if all that could be comprehended by a intelligence, then it would embrace in the same formula the movement of the greatest bodies of the universe and those of the lightest atom. He means that there could be just one set of equation that will describe the dynamics of not only small bodies like atoms, but also large bodies such as the heavenly bodies or the planets in the universe. All that could be described in a single set of equation and it could be solved. And if that can happen, then he says nothing would be uncertain in the future and the past would present to its eye. So he's talking about there could be an intelligence which can comprehend all the positions of all the atoms and molecules in the universe, and it can also understand all these different kind of forces acting between them. Then when subjected to one universal dynamical equation, then it's easy to predict what's going to happen in the future and what has happened in the past as well. So that is a kind of vision that Laplace had, and what we are doing in molecular dynamics simulation is partially fulfilling his vision, in the sense now the intelligence now is basically nothing but computer. Okay, now the computer can actually, we can ask the computer to calculate these forces, and it can actually store in their memory what is the particle position and the molecular position, and then we can actually dynamically we can evolve the system to predict its future. So the molecular dynamics simulations in principle is actually have been already thought through in Laplace time itself. And what we are just doing now is that we are at a stage where we have very powerful computers which can actually do this partially. And you might also wonder whether this dynamics of this greatest bodies and atoms, do they really follow the same set of dynamical equation. Maybe at that time quantum mechanics wasn't known, so he might thought that everything could be described in a classical mechanical framework. But now we know that atoms have to be dealt differently in quantum mechanics, whereas classical bodies and heavenly bodies could be still dealt with classical mechanics such as Newtonian mechanics. Alright, so I'm trying to now put together again a picture here, showing you what is the link between experiment, computer simulation and a theory. So generally you start with a physical system which you want to investigate or you want to study. The easiest thing is to perform an experiment, given that you have all the wherewithals of doing this experiment. And then after conducting the experiment, you basically collect a set of results or facts. This is one way of conducting research. The other way is, for the physical system, you first make a model. Reality may be presenting something, but then when you want to translate into a theoretical or computational approach, you want to build an analogous model, a simple model, and that's what we call as a model system that mimics the behavior of a physical system. So then you can construct a approximate set of theory. These theory could be statistical theories or principles of thermodynamics could be used, or any other set of kinetic theory of equations can be set up, and then you try to either analytically or numerically solve them and make some theoretical prediction of the behavior. And now you have two sets. One is experimental results, other one is this theoretical results. So now traditionally we have been comparing the experimental results with the theoretical results, and if experiment and theory matches well, then we can agree that this model system we have hypothesized is correct. If the results of experiment and theory did not agree well, then that means that the model that we have built here is not adequate enough. So we go back and then change the model system to include certain parameters that are essential for this particular system. So now the computer simulation basically comes in between. As you can see here, we take the same model and we basically remove all the limiting assumptions made in the theory, but we try to exactly solve the system using set of computers, and then solve for exact results for this particular model. So now we have three results: experiment, simulation and theory. So now this simulation basically helps us to compare the experimental results or with theoretical results. So thereby this computer simulation nicely fits in between experiments and theory to validate the theoretical predictions, at the same time also trying to explain the experimental data. So that's why the computer simulation is actually has become one of the most important scientific method of investigation. Whenever there is an experiment or theory, we often take help of computer simulation to support the results. So now when we talk about molecular dynamics simulations or computer simulations in general, the first thing we need to do is what kind of length scale and time scale are involved in the physical phenomena that we want to investigate. And this basically takes us to this particular diagram, where on the x-axis length scales are written, on the y-axis time scales are written. In this case, the length scale varies from nanometers to millimeters, and the time scale it goes from femtoseconds to seconds. So now you can see that when you're looking at a very small length scale and small time scale, we are in this quantum regime. Okay, so in this quantum regime, the dynamics are pretty much dominated by electronic transitions. The electronic degrees of freedoms are important. Much of the change that happen in the system are governed by electronic dynamics. And then if you go to a little larger length scale, between nanometer to a micrometer, and then similarly from picoseconds to microseconds, then you have this regime which is called the atomistic limit. Okay, so in this atomistic limit, the electronic degrees of freedoms are not so important. You can actually discuss the dynamics of the system using the nuclear position of the atoms and molecule itself, and this is where we can even use classical mechanics to study the system's behavior in general. And then if you go to a little larger time scale and length scale, then you get into what is called coarse-grained and mesoscale limit, where the system is not as small as atoms and molecules. It has become a little larger. Some of the processes are happening at a larger time scale and a larger length scale, and then we have this set of mesoscale regime. And then the last point, the corner of this, is called the continuum limit or fluid mechanics limit, where the time scales and length scales are little larger. So length scale can be millimeter and beyond, and time scale can be seconds and above. So any engineering problems, fluid mechanics or heat transfer that happens in a large amount of substance could be dealt with continuum mechanics. And now in this case, I have also given some examples taken from biophysical field. What are the processes that are taking place at such small time scales and length scales? For example, if you look at the femtosecond processes, these involve bond vibrations. So the bond between two atoms, and if you look at the time scale at which the bond vibration can take place, that happens in about femtosecond time scales. And then if you look at diffusion, diffusion typically takes about picoseconds and little above that. And then you have protein folding, which takes about microsecond and beyond. And then DNA replication or membrane fusion, these are happening in a much larger time scales. Similarly, if you look at length scales, the sub-nanometer length scales are in which the bonds are relevant. If you want to study the bond formation and bond creation, then you talk about very small length scale. And then if you look at the lipid rafts, then we are talking about sub-micrometer length scale. And then if you go to vesicles, which are little larger objects, then you're talking about tens of micrometer and even beyond. So now, when you look at any computer simulations, we want to basically look at what length scale and time scale we are going to investigate. As far as MD simulations are concerned, we are basically in this particular limit, which is called this atomic limit, and to some extent even the coarse grain limit also. Okay, so any physical process in which the length scale varies from nanometers to micrometer and time scale from picosecond to microsecond, we can fairly use molecular dynamics simulations. If you go below that, then you see that the electronic degrees of freedom become important, then classical mechanics will not work, so you have to use quantum mechanics. Whereas if you go to the other side, then the amount of the system's size and the process that takes place are going to be extremely large, and computer simulation will not be able to afford to reach such a large time scale and large length scale. So we don't want to do computer simulations neither in this regime nor in this regime. Okay, but anything in between is okay. So that's something as a student would like to remember when to use computer simulation and for what kind of processes. Now, here I have given some summary of various fields in which computer simulation have been used, and all these examples are taken by keeping in mind that all these physical phenomena takes place on length scale, time scales that can be reached by computer simulations. So typically as of now, even though we have all these powerful computers right now, doing atomistic simulation or molecular dynamic simulations beyond microsecond is still limiting. And similarly, the length scale you can go is up to tens of micrometer, and if not beyond. And then in the future, if you have much more powerful computers, we may be able to even push this boundary of going to larger time scale and larger length scale as well. But what I have given here is a set of examples in which molecular dynamics or computer simulation in general have been applied. In the very beginning, the interest was looking at fundamental studies of liquids, looking at structural and transport properties of simple liquids like argon or water have been studied, and some simulation to test the kinetic theory, even to test certain models and potential function have been used. So that's a very beginning how MD simulation got into this research areas. And then people were interested in studying phase transitions. That means when a substance exists in more than one phases, liquid vapor or liquid solid. So there was some interest to study the nature of these transitions. So first order and second order transition have been studied using molecular dynamic simulations, phase coexistence, order parameter that characterizes each phases, which could be density or other parameters, and then even critical phenomena. So these are some of the phase transition problems that have been addressed by molecular dynamic simulations. And major advances happened from biomolecular systems. In the very beginning, people are wondering about what is the nature of protein, how does it fold, how does it function. So, and protein is much larger molecule. At that time, studying, understanding protein from experiment was not possible. So they were looking at some computational methods to study structure and dynamics of proteins. I will show some examples in the coming slide. And also about surfactant micelles, lipid vesicles and membrane are also some of the topics that have been studied in the earlier times. So not only the individual molecular and molecular system, but also collective behavior have been also studied, which involves calculation of correlation functions, dielectric properties, sometimes spectroscopic measurements, self-assembly of particles, surfactants, aggregation of nanoparticles, and polymers. So these are all some of the systems that have been studied in a collective behavior. And then complex fluid is another emerging field. So complex in the sense, it could be having multiple components, and it might have solutes which may vary in sizes. Okay, you can have a combination of surfactants and nanoparticles, or polymers and nanoparticles, okay, which are very different in their size, but they all kind of immersed in the same background solvent. And then you see that this complex fluids behavior is very non-Newtonian, and you want to study their mechanical or transport properties. So in this complex fluid domain, a lot of work has been done on understanding dynamics of gases, even simple liquids like water and ionic solutions, aqueous solutions, liquid crystals, ionic liquids, thin films, surfactant monolayer or lipid monolayer, and wetting of a droplet on a surface. So these are all some of the examples of complex fluids that have been studied using molecular dynamic simulations. And polymer is another active area in which molecular dynamic simulations have contributed enormously in understanding their physics, which involves studying equilibrium conformation of large polymeric molecules, predicting their mechanical properties and as well as transport properties. We invariably use polymers in various applications. Looking at their mechanical behavior and transport properties are extremely important, and it's still an active area in which molecular dynamics is very important. And molecular dynamics also has been used in studying solids in terms of how defects are formed and what the fate of the defects, how grain boundaries are formed and how do they move about, and even looking at radiation damage in solids and metals, in general predicting mechanical properties, even growth of solids via epitaxial growth. So these are some of the other problems in solids have been addressed using molecular dynamic simulations. There are also some fluid mechanics problem done at a very small scale, looking at laminar flow, the formation of boundary layers, and then rheology of non-Newtonian fluids also have been studied. So these are all the problems that happens within a small length scale and time scale. But then there are also other systems like plasma and modeling of galaxies and semiconductor devices. These have been also used, have been studied using molecular dynamic simulations by making certain coarse grain approaches. Okay, so there is no one-to-one correspondence between atoms and molecules in the MD simulations, but then you group set of atoms and molecules into a larger object, and then you do some sort of coarse graining, and then studying of this large scale phenomena is also possible in some special cases. This is not very general, but some special cases have been done. So now I want to show some pictures of how MD simulations have been important in giving some physical understanding, deeper understanding of materials in general. So here I have deliberately taken examples from one of the first few simulations in the literature. If you look at this particular picture, on the left hand side is a dynamics of a solid phase. On the right hand side you have a dynamics of a fluid phase, and what you see, this jiggling motion here is basically atoms are placed in a lattice, and then you look at how the atoms move in a solid material, and you can see the atoms are jiggling about their position, but then they are not diffusing away. Okay, so they are bound to the lattice points, but they are very agitated and they are jiggling around their lattice points. So that's how you look at that. That's how you think about how a solid would look like microscopically. And whereas if you look at fluid phase, in other words liquid phase, you see here, even though you start with the initial position and the atom starts moving about, okay, they start diffusing about from their initial position and they continue to diffuse. So they do not remember what was their initial condition was. They continue to explore whatever space that is available. So this jiggling motion, constantly colliding with each other, is a very characteristic of a liquid behavior or a fluid behavior. So in 1959, this is the first simulation that was done to understand the microscopic details of seeing a liquid and a solid in a computer simulations. So you can see the computer simulation or molecular dynamics simulation in this case have given a clear picture of what is the dynamics of atomic motions in a solids and a fluid phase or a liquid phase. So this has been one of the key MD studies in the beginning that has began to benefit a lot of other studies that came up in the later times. Now here, in about 1964, in another study, the property of liquid argon was studied. So argon, as you know, is an inert gas, but then if you go to very low temperature, you can liquefy it. And then at that time, there was some experiments available to study what is the diffusivity, self-diffusivity of liquid argon, and what is the structure of this liquid. So the structure of liquid is actually characterized in terms of what is known as this radial distribution function. These things we will discuss later, but for time being, what I'm trying to say here is, if you look at one particular argon atom, and then if you radially look outward and you see how many number of neighbors are there in a given distance, that's what called a radial distribution function. And you can see that if you sit on one particular atom and if you go radially outward, and then you see that there is a first layer of neighbors, which is called the nearest neighbors, and then second nearest neighbor, and then third nearest neighbor. So this is something you can experimentally obtain using scattering studies. And this Rahman et al. Basically studied the same argon system in a computer simulation, and you can see that the structural properties obtained from simulation and that is obtained from experiment are basically matching very closely. Not only the structural features, but also you can see that self-diffusion coefficient of liquid argon at two different thermodynamic conditions have also been nicely matched between experiment and simulations. So what this example tells you is that it is possible to construct a model for a real system, in this case liquid argon, and then carry out molecular dynamic simulations, and then you can actually predict the transport properties and structural properties, which is exactly matching with experiment. So MD simulation can in principle give you a quantitative prediction of experimental results. So this is a more like a benchmarking. Once this is done, and if you want to look at liquid argon's behavior at a different thermodynamic conditions, you don't have to go and do experiment one more time, but you can just run a simulation, and then you can calculate what the properties are going to be. Okay, so that is the power of computer simulations in predicting the structural and the thermodynamic behavior of materials. So here is an example of radiation damage on metallic copper. So we have a copper crystal, and all this, the bigger circle that you see are basically the initial position of the copper atom in a lattice in a particular plane, 100 plane, and then there are some smaller dot here. So these are all the atoms just below this plane. Okay, so you are talking about two layers, top layer and bottom layer. Top layer are shown in the larger circles, and the bottom layer is shown by the smaller dots here. And then radiation is actually shone on this particular material, and we would like to see what damage happens in this material. And then if you look at one particular trajectory, initially there is an atom at this point A, and what happens is when this radiation is exposed to this material, and this atom basically moves here. Okay, and the atom that was here moves here, and then the atom that was here in C moves to this interstices point. In the original before exposure, this point D was empty, but now because of this radiation damage, you create a vacancy here, and then you create a interstices here. And then you can see also the effect of radiation is not just localized only here, but you can also see the atomic motion of the nearby atoms also, whereas there are atoms far away which are not affected by radiation. So this gives a very clear visual picture of what is the fate of the atoms when exposed to radiation. So this kind of a microscopic picture is basically able to we can get it from MD simulations. So this is one of the earlier studies looking at a protein folding problem. So in this case, a very small protein called pancreatic trypsin inhibitor known as PTA. The structure is shown here. So people are interested to know how does this protein fold and what's the time scale associated with folding such protein. So to do this, this is a real protein, and they build a model. Okay, so remember I was telling you about that before we go to a computer simulation or theory, we have to translate the real system into a model system. This is what it is. So whatever the chemical details that are there are now simplified into a set of a backbone chain, and then all these side groups are given by a simple a bead hanging on the backbone chain. Okay, so now you look at how what is the interaction between these different residues and what is this angled potential and what's the dihedral potential. So everything goes in there, but you can see that structurally, topologically, the model mimics that of the protein, but the model does not have many finer details of what is the structure of this residues and what are the atomic level details of the residues. Those are not important. So what is important is this topological information is sufficient, and initially you start with this kind of a fully extended chain like this, and then you do this computer simulation on the system, and then you can see how nicely the protein actually folds as a function of time. Starting from this linear structure, it goes into a very nicely folded structure and in about a microsecond time scales. Okay, so this is one of the very first studies on looking at MD simulation of protein folding problems. So in the previous example, we talked about the structural or folding dynamics of a protein. And another question at that time existed was, if you look at a folded protein and the question is, inside the protein, what is the motion like? Is it frozen like a solid, or is it a very liquid-like behavior inside? So that was a very long-standing question, and experimentally it was not able to investigate at that point of time. So then people did MD simulation of such protein, and then what is being found is that what you see in the left-hand side, all these graphs are basically correlation functions, and you can see these correlation functions decay. So when a correlation function decay in a very short time scale, like in picoseconds, it basically means that the interior of the protein is a liquid-like or a fluid-like. This is one of the very important results that was obtained only through MD simulation, because at that time experimental means were not available at the time. But now you can do NMR and other kind of advanced techniques to study. But then back in 1977, computer simulation was used to study the protein interior dynamics. And here is another example looking at what is the behavior of surfactant when you mix them with oil and water. So, surfactant is basically a chemical molecule which has a hydrophilic head group and then hydrophobic tail group. So this is hydrophobic chain, long chain. So this chemical molecule is now put into a simple model which is shown here. You can think of this single chain. So these 4 beads here are basically mimicking the hydrophilic groups, and this long chain shown by black dots are the hydrophobic chain. And you can make multiple such as surfactants, 2-chain surfactant, a 2-chain surfactant with a spacer between the head groups, and there are some various other models. And in this particular paper, they looked at behavior of such model surfactants in a oil water system. And you can see that if you look at this particular picture, you can see that on the left hand side you have an oil phase, on the right hand side you have a water phase, and all the polar groups are facing the water side, and all the non-polar or hydrophobic groups are facing on the left hand side. So if you look at the interface, one side facing water in which all the polar groups are arranged, on the other side, which is oil, all the non-polar groups are aligned each other. So this gave a very nice picture of the way how the surfactant adsorbs to a oil-water interface through computer simulations. And in this example, the adsorption of methane gas in zeolite, which is an adsorbent, is studied. And in this case, what is shown is the experimental data is shown by the red squares that you can see here. And then a simulation was done with various different kind of models. Okay, so like I said, a real system has to be converted into a model system, and how we do that is a little bit arbitrary, but with experience and by intuition, we can come up with more closer model to the reality. So in this particular example, you can see all these different simulations with the different models, even though they predict a very general behavior, that if you look at the shape of the curves is very similar to the experimental behavior, but then quantitatively only 1 or 2 simulations predict, whereas other simulations are quantitatively different. What this basically means is that when you build MD simulations, that's why sometimes it's called MD simulation is called the art of doing MD simulations, because sometimes there is a little bit of arbitrariness how we want to develop the model to mimic the reality. So in this case, the model by this M5 and this particular work seem to be nicely correlating with the experimental data around there. Okay, whereas these 3 models seem to be little away from the experimental data. So this tells you that how one has to be careful about building the model so that the experimental comparison can be achieved. So now, even though I have been advocating the use and benefits of MD simulations or computer simulations in general, this technique is not without any challenges. It does face a lot of challenges, and we have to be cognizant of these challenges whenever we try to apply molecular dynamic simulations. So for example, one of the problems that you will face is the formation of multiphases. So when you want to study multiphases, for example, it could be a liquid gas, or it could be a liquid solid, then in the simulation itself you will see the thickness of the interface itself dominates the entire system size. Then the data that you get from the simulation becomes little less reliable. So it becomes very important to avoid such multi-phase problems when you do simulations, or you have to look at a very large system size so that multi-phase problem can be analyzed. So you have to be very careful with whether you're simulating a single phase or multi-phase. Many times we would like to basically create a inhomogeneity in the system. For example, you may want to create a density gradient or a temperature gradient, and you want to look at some heat diffusion, heat transport or mass transport. So in such a case, creation of this maintaining this gradient across the simulation box becomes a little challenging, because the simulations will show a lot of fluctuations, density fluctuations and temperature fluctuations, and try to homogenize it. So whenever you want to study inhomogeneous systems, again one has to be extremely careful whether your system size is enough to handle such situation or not. Many times we study systems which relaxes very, very slowly. Example could be a glassy state or amorphous state, or a system in which there is some rearrangement that happens in a very, very long time scales. So whenever you have such a slow relaxation time, you have to be careful whether your computer simulation is enough to address such a problem or not. This we already have talked about during the time scale length scale issue, but I'm trying to reiterate here. There are certain processes which are known as rare events, because these are activated processes. There is an energy barrier to cross, and when you try to apply MD simulation for such rare events, you will see that your simulation does not really show any changes in time. So it will look as if the system is stagnant, not moving to a new phase or something. So example could be a nucleation problem, or escape from a potential well. So because these are all having very large energy barrier, again there are methods to handle such rare events via some smart techniques, but brute force molecular dynamic simulation will be extremely useless when you try to look at rare event simulation like this. So we have to resort to some special techniques in such cases. And sampling is another big issue, because whenever you draw some meaningful measurements from your MD simulations, you have to be absolutely sure that you are able to do adequate sampling so that you are able to get reliable results. So extra care has to be taken into, so that the sampling is sufficiently carefully done. And finally, the computational resources is another limiting factor. Even though we may have a powerful computers right now, but the amount of memory required, the amount of CPU time required, these are all going to scale with respect to how big the system size that you're going to take. So we have to always compromise between how much time we have and how big the system we can simulate. But again, despite all these challenges, all the examples that I have shown before have given meaningful results to our understanding of physical sciences. And we have to just remember, these are some of the challenges that we have to keep in mind whenever we try to resort to computer simulations. So with all this information, so I would like to basically summarize. Computer simulation basically it helps us to predict and interpret our experimental results, and it also validates theory. So that's the most important things that we want to remember. And sometimes the computer simulation can be exploratory. That means it's not that you have to wait for experiment and theory to be available so that computer simulation can be done. You can even go ahead and conceive a situation and you want to ask what is the expected results. So that's when this research becomes exploratory. And if you get some meaningful results, that can be inspiring for an experimentalist to try out such an experiment and see whether such a new investigation can be explored or not. And this is a rule of thumb. The physical phenomena that happens in about nanometer to micrometer and picosecond to microsecond. So that's the typical time scale and the length scale limit that we want to apply MD simulations. But this is a general guideline, but there are also exception to this. But it's good to remember this particular range of applicability of MD simulations. And most importantly, like experiments, simulations also are subjected to statistical analysis. That means whatever you measure in your MD simulation should be subject to statistical analysis, reproducibility, and sampling, so that the data that you derive from MD simulation is useful and meaningful. Okay,